So, anybody have any questions about anything so far? Okay. All right, we'll just launch off here. There's a few things to know about this stuff. It's not exciting stuff by any stretch of the imagination, but stuff you need to know about. Yeah, a couple of things to know about here. So the connecting rod is what links the piston, which moves in a linear fashion, to the crankshaft, which moves in a rotary fashion. We're going to have one rod per cylinder, one rod per piston. Now, the way most of these are made in the reciprocating engines, they're split around the crankshaft. How they do that is they use a rod cap. Now, it used to be that these rod caps, they're all machined in one piece, and then they saw it, and then they'd come back and refit it, rebore it. Because when you saw something out, you have what they call the saw curve. And that's the thickness of the blade that you use to saw it with. So they do that, and then they have to come back and rebore this thing so it's completely round. Well, if you take and explain that a little further. So you've got a perfect circle, and you take a cut through it. The thickness of that cut is going to move, when you bolt it back together, it's going to move both sides back together. Do you have a concentric circle anymore?
Mm-hmm.
No, you don't have a concentric circle anymore. So now what you've got to do is you've got to come back and bore it again to make it concentric or round. Right? They don't do that anymore. Now what they do is they split these. And it makes for a somewhat imperfect looking joint between the cap and the rod. So most of the newer ones now are split, but you don't lose anything when you do that. So they crack it just like glass. They put a score in it and they crack it just like glass. So the two pieces fit back together. They don't have to go back and rebore it. And one of the things that does is that surface between the rod cap and the rod itself now fits even more perfectly, because if you split it, it doesn't create a super smooth surface like it does when they saw it. So it has little ridges and valleys in it, but when it goes back together, it fits perfectly because they haven't removed any metal. Y'all see that? Now that's on the most modern rod caps. The older ones you'll see, they have tool marks up here on this surface. And those tool marks indicate that they've been sawn. So there's something that's really important about this is when you put these back together, whether they're sawn or cracked, they have to go together in the correct assembly. So when you find these things, and you can peer down into your engine right now, you can see it, is that you're going to see a pair of numbers stamped on it. This one here is stamped 4 and 4, so they have to match. You want the 4 and 4 together. You don't want the 4 on one side and the 4 on the other side. It's a 4, it's a 3 or 2 or 1 or whatever. What that does, that tells you the location of this rod cap, what rod that it goes on. It also tells you or gives you a hint as to which way these are assembled. So if you come back and you bore this hole, one half it somehow gets flipped and going the other way. Now that hole isn't concentric anymore because it was bored or it was made concentric when these were assembled. So they'll stick a bolt in them, bolt them together, and then they'll go through and they'll reassemble them. Okay? So know that that's one little thing you have to remember. All right. So we split them to fit around the crankshaft. We can't slide them over the crankshaft counterweights. The hole just isn't big enough to do that. Our radial engines, we're going to use what we call a master rod. The master rod looks like this. And it's going to have the attach points for all the other rods that go to the other cylinders on the radial engine. And those rods are called link rods. So those link rods all fit. Those link rods all fit like this around this thing. Only one of these on a radial engine, only one of these is going to make a perfect circle. I'll show you in a second. Know that you have a master rod and you have link rods on a radial engine.
Is there only one crank throw?
What's that?
So is there only one crank throw per bank?
One crank throw per bank. Yeah.
Okay.
Okay. So this is what they're going to look like when they're all put together. This one only has one rod attached to it, but it would ordinarily have a rod in each one of these holes. This is also known as a banjo from its odd shape. Now, those can be assembled two different ways. So the connecting rods that we use on the opposed engines have split caps. Some of these use split caps, like this one here. Some of them, you take the crankshaft apart and then you put it back together through this hole here. So this one is not split. Y'all see that? Y'all see that?
Yes.
So the master rod's one piece, most commonly. It can be split, but most commonly it's not. The crankshaft moves in a circular orbit, but on a radial engine rod assembly, only one is going to move in a circular orbit. I'll show you. I got a little animation here to show you that. So the link rods, all the other little rods that attach to this thing, move in an elliptical orbit. Now that's going to change the timing of the engine just slightly, just a little bit. Because at some parts of the orbit it's going to move faster, and some parts it's going to move a little bit slower. So things speed up and slow down, whereas this one here moves at the same pace all the time. But that's all compensated for inside the engine insofar as timing and valve adjustment goes. So there you are there. You just take your eyes, I don't want to hypnotize any of you. But this is what's going on inside a radial engine. If you follow the greenie here, the greenie's going to move in a perfectly circular orbit. But if you look at any one of the other yellow pins, you'll see that they move in an ellipse. You'll see that? It's one of the idiosyncrasies of a radial engine. So that's going to change the timing of the engine ever so slightly for the other four cylinders in this case. So this is a 5-cylinder radial here. Interesting. We don't have to worry about it so much, but know that only one travels in a circular orbit. And that's an FAA test question, by the way. So there's another design called a fork and blade design. So this. That's used with some V engines, some V-type engines, where the banks are arrayed in a V fashion. In this case, both of these rods are attached to the same crank pin, and they both go in a circular orbit. I'll pass you tonight and look at these. It's a blade and fork design.
What are those out of? What are those out of?
Those are out of a Harley.
That sounds about right.
until the engine gets up to speed, it creates kind of an uneven loping sound. Well, you heard a Harley before, right? And that's what you get with a Harley. You get that uneven loping sound until you get the thing up to speed. Now you hear this on other B aircraft engines as well. They kind of lope along. An Allison or Rolls-Royce B, same thing. There are a lot of those still around.
So those you have to disassemble the crank.
Yes, split the crank. Now, connecting rods can be an I or H configuration. And that is with respect to the pin alignment. I'll show you a picture here in a minute. The piston end is going to have a bushing in it. Won't have a bearing in it, just a bushing. Most ordinarily, these rods are forged or cast steel. Some of them are aluminum. They shot peen the surfaces for increased strength. I talked about that the other shot peen.
Yes.
What that does is it normalizes all the stress after the machining operations in the forging operations that take place with the part. So here you have an I-type, and again, this is with respect to the pins that run through it. So you can see which way the pins run. This is an I-type rod. The pin orientation through this is this way. You all see that? And if you were to cross-section this, you have an I-shaped rod. Now, they make these in an H also. It's somewhat easier to fabricate one style than the other, but Pratt & Whitney and Wright and some of these other companies choose to go their own way on this. They feel that they're stronger one way or another. It really doesn't matter too much. There is an H type, so the pin orientation is this way. And if you look at that, it's an H shape if you were to section this thing. So there's an H shape right aeronautical banjo. Y'all see that?
I don't see how you see the H in there.
What that shows you is the web on inside. So you have the two sides here, vertical sides here, and then the web going across the middle.
Oh, okay.
You can see that?
Yep.
Okay, so Jude, what shape is this one here?
I.
What, slappy?
H.
There you go. Try again, yeah, right, there you go. Okay, so it's this one here.
H.
Okay, what's this one?
I.
There you go. Okay. So I just planned this slide just for you. Do y'all see that? I and H configuration. This is so important. Okay, you're working on an engine, it's no big deal. You're going to put all the same stuff back in. You're not going to be substituting stuff. But where this comes in to be a problem is that if you are working on two engines and have parts for two stands, you don't want to mix the two parts up. Right? Now, a lot of these will fit one another, but they're not supposed to be put together that way. Okay, so when you clean a connecting rod, it's by primary or secondary methods. So this is soaking and scrubbing. First two methods are soaking and scrubbing. You don't use any kind of mechanical cleaning on these things. You're not going to do any bead blasting on them of any kind. The surface finish is super important on these things. And after you finish with them, put a little bit of oil on them. So the engine that you're working on outside, take a little bit of oil in your hand, wipe these things down so they don't rust while they're laying around on the part stand. Okay. Do that to all the parts when you take them off. That will keep the rust at bay. Okay, so the inspection of these things. It's going to include the visual, Magnaflux, alignment, and dimensional. Land will show you how to do the alignment check. Magnaflux is pretty straightforward. You all do those in general. You're going to be doing a visual also and dimensional checks on them. And I'm going to explain these. So the visual, you're going to be looking for nicks, cracks, scratches, anything like that. Don't mark them, handle them carefully, don't drop them on the floor. There should be no fretting wear across this surface where the rod cap and the body of the rod connect together. If there's fretting, what does that indicate?
Something's wearing.
What's that?
Something is wearing.
Something's wearing, something's pounding, and what'll happen is these things kind of sit there and chatter sometimes because the bolt's not tight. Shouldn't be any abrasion on them. And these are usually come in a set. When you buy them out from a manufacturer or you're doing an overhaul, you'll buy a set of connecting rods if you need them. Most of the time you don't need new connecting rods, but you have to do the inspections on them. You have to replace the bushings, you have to replace the bolts and the nuts, but most of the time the rods are just fine. Also, again, that journal where it's split, make sure it goes back together the same way, number to number. Now, sometimes these have to be installed in an engine directionally. You got to say numbers up or numbers down. And that will depend on the manufacturer. So you have to look at this, check for it on disassembly, but also look in the book. The book will tell you. And the reason for that is because they have an oil hole in these things. And these are for lubricating the engine. And if you put the hole on the wrong side, it doesn't splash out in the right direction. So you have to put these on the correct orientation. So make sure you check the book before you put your engines back together. Also, you want to look for any kind of temperature coloring in the big end or the small end of the rod. You start to see bluing, what's that going to indicate? Indicate it got too hot, right? So there would have been a lack of lubrication for some reason. So Magnaflux. So this is magnetic particle inspection. You're going to be looking for cracks at the journal bolt flares, and these are going to be the cracks right in this area. This up here. And through this area right in here, and this is where the bolts clamp these two halves together. So when these bolt halves or when these halves are clamped together, if they're not clamped together tightly, they start to work back and forth, and that's what will precipitate a crack in these rods. This is all stuff you're going to be looking for. But any kind of visual crack is pretty easy to see, but that's why we use Magnaflux, because that's going to detect any hidden cracks in the surface of the metal. Okay? You're going to be looking across the web flanges. That is to say these areas here. Across here, you're going to be looking through this area here. The journal bolts and an overhaul are going to be replaced. Now these can also be checked for stretching. If you have a bolt stretched, what would be the upside of that? What would be, so you have a bolt that's stretched. What's that going to do to this assembly in operation?
It's gonna
It's going to be loose, right? So this thing is going to the top of its throw, it's going to the bottom of its throw, stopping, turning around. going to the top, stopping, turning around, going to the bottom, stopping, turning around. And so what's that gonna do eventually to this thing here?
Loosen it up, make it bigger.
It's gonna start working loose. And when it gets loose, it's Katie bar the door. Because what's gonna happen is these things, usually what happens is they break before they come apart. And when they break, now you've got this thing flailing around inside the engine, and it will cut the engine in half. Okay. So each part, so far as Magnaflux goes, should be checked separately. Don't put the rod in assembled because you won't see everything you need to see. Alignment. So we have a tool outside, and Land will show you how to use that. It takes a feeler gauge, it takes one fixture tool with it. Now what you're gonna do is you're gonna check these for twist. You're also gonna check them for bend. So throughout their lifetimes, bad things happen to these things. These two holes should be parallel to one another. Okay. Parallel this way and parallel this way. Okay. If they're not, you've either got a bend. If they're not parallel this way, that means that they've gone like this and have a bend in the rod. Y'all see that? Mm-hmm. If they're not parallel this way, that means you've got a twist in the rod. So we have a fixture tool to use with this stuff, so that you can determine if there's bend or twist in it. And when you check the rod, you should have the cap on. You take the bearings out because the bearings will get cacked up if you put it in the fixture with the bearings. And the bearing material is fairly soft, and so what it does is it springs apart, puts a load on this thing to hold it still, and you'll ruin the surface finish on the bearings. So be sure that these are bolted together. They don't have to be torqued, they just need to be snug. Okay, this is what the tool looks like. Some of you have seen this thing over there. Have you seen this thing over there outside the shop? Pay attention, you'll see it out there. You'll be using this this next week or two. So it depends on how the pin is secured in the rod. It is going to depend on how you use this alignment tool. There's a couple of fixture tools that go with it that support the piston and measure off of the piston. But you only need the one because all of your wrist pins are easily pushed out of the ends of your connecting rods. So we can do one with the connecting rod and the wrist pin together. We could do one with the piston attached. Sometimes the pistons are kind of hard to get apart. Everything's pressed together, so they have to be done attached. You don't have to worry about this one here. This is the one that you're going to be using when you have these parts in the tool crib. So once you get the engine split, we'll be showing you how to use that. Now I have to tell you too, you might pay a little more attention now, is that this is one of your core questions on your final exam in the lab. We'll be doing dimensional checks. You're going to be measuring the OD of the pin. You're going to be measuring the rod journals. You're going to be measuring the clearances between the crankshaft and the connecting rod. When you measure the connecting rod, you got that hole in the big end, you got the hole in the little end up there. Make sure that you measure across in several different dimensions or several different axes. All right. You're going to be doing this with the bearing in it. You're going to also be doing it with the bearing removed from it. Now what you're looking for is going to be stretch. So these holes should be concentric. If you find any stretch, which dimension would it be? Clock position would it be 12 and 6? Would it be 3 and 9, 4 and 10? Which way would it be? Anybody? What is it?
3 and 9.
3 and 9 is across this way. Think about that. So this thing fits in the engine this way, goes this way, this way, this way. So which way is probably going to be knocked out of shape? 12 and 6. This way to this way, because I moved it. Okay, so clock dimension now, so laterally this way, right? So it's going to be probably knocked cuckoo this direction here. Because remember, this thing is always going out, stopping completely, and it's going back, stopping completely, it's going out, stopping completely, and so on and so forth. So the pressure is always in this zone here, and always in this zone right here. This spot? Everybody got that? You're gonna be looking for taper, not around. That's gonna take care of that. You're going to check for any kind of rod stretching or compressing. So there are fixtures that you put these things in to check them for lengths, the center line from here to here, but I'm going to let you do that dimensionally. You guys are going to measure the diameter of the hole, find the center of the hole, and then find out all of these have the same centers. Does that make sense? These things are stretched, they're probably going to be stretched, they're not going to be so much compressed, but they may be stretched. Right? So you're going to have to measure dimensionally, find the center hole here, center point here, measure center point here, and compare all your rods together. And as it says here, measure with the old rod cap, or your rod cap, tighten to specs, so it should be pretty darn snug. Now, when you put these things back together, you would, we're not going to because it's kind of expensive, but you would use new bolts. Now, a lot of these bolts are torqued. You torque them with a nut. So a lot of them have castellated nuts. And you put a cotter pin in it. That's an older style, but all of them now use a self-locking nut. The self-locking nut tightens it down to a torque, and then you're going to check it for stretch. So you're going to actually measure the length of the bolt to make sure that you have the correct lengths on it. You won't know what the torque, whether the torque is correct or not, unless you check the rod stretch. There's a couple of different ways to do that. Check your book. Okay, so the repair of the rod is going to include replacing that bushing. It's just an oil-like bushing up in the top end up here. It's a little cheap bushing, costs only about $5 or $6. They press this in, press the old one out, press a new one in there, and then they hone this to the right diameter, the right inside diameter, so it's just a thousandth or two clearance on the rod gem. You're going to renew the bearings in here as part of the overhaul. New caps, new bolts for the cap, new nuts, attaching hardware. If it uses castellated nuts or cotter pins, all of that will be replaced too. Now the bearing insert that goes into this is two pieces. It's a shell, two shells. Half fits in here, half fits in the other side, and the cap goes back together. It's kind of a pinch fit, and it doesn't really go round until you squeeze the bolts down on it. So it's kind of an arch shape. As soon as you pinch the bolts down, it pushes it up into the shell and into the connecting rod. That makes it round. Now the bearings that fit into these have lock tabs on them. And the lock tabs engage, pass this one around. The lock tabs engage, there are some notches in the rod itself and in the cap that keeps the bearing from spinning. So if the bearing gets a little dry, or the bearing begins to because to try to grab the crankshaft for any reason, it can't turn. It's locked into the rod itself, can't spin in there. Now, some of them are opposite sides, the rod and the cap, some of them are on the same side. Just know that if you have the numbers together, you're going to have the correct orientation for the bearing. And we'll look through that pretty quick. Okay, so it's connecting rods. An exciting world of connecting rods. Somebody wake him up, you miss the excitement. You guys got any questions about connecting rods? It's not much to them, pretty simple. A few little things you need to know. Yeah.
I still have a hard time really getting the difference between the I and the H connecting rod.
Yeah.
I
Look at
understand-
that one right there.
I understand you could see it that way and holding it up, but oh, it's just like it actually helps like press it.
It's with reference to the hole.
But it doesn't have like a different application and different engine.
No.
Okay.
Nope. It's just a different manufacturing process is all it is. Anybody else?
Just 1 second on the slide.
Get it? Okay, let's go back to crankshafts. This is not much more exciting. Connecting rods. Maybe a little bit. So what you're going to do with your engines is you're going to split them. They have a split, what they call a split line on the two case halves. The two case halves, as you see it from the outside, hold the light part of the case together, but the major part of the structure of the case is held together with the through bolts that go through the cylinder. So you all remember those bolts, right? Big bolts, big nuts you took off the cylinder bases. So those bolts go all the way through the case to the other side. And that is what clamps the case together and supports the crankshaft. So the crankshaft runs in the case. Also, the camshaft runs in the case. So the crankshaft runs on bearings, soft Babbitt material bearings, B-A-B-B-I-T, runs on soft Babbitt bearings. The camshaft runs right on the aluminum case. It is lubricated. There's an oil gallery that feeds the camshaft where it rotates in the case. Doesn't wear the case out at all. It runs in quite a lot of oil. But you have so much more pressure acting against the crankshaft because of the piston movement. The camshaft doesn't have all that pressure. So this is the piece that's going to take the pistons movement and the connecting rods movement and turn it into a rotational motion. This is the one that's going to give you the power to run a propeller, to run a gearbox, transmission, maybe in a helicopter. Most of these crankshafts are hollow. What that does, it cuts the weight down, it increases the strength. We also use the hollow galleries inside the crankshaft for flowing oil, for lubrication, and also for heat transfer. So we can knock a lot of heat off the crankshaft by running oil through it. So the oil not only lubricates, not only cleans, but what else? Cools. aircraft cranks, size for size, are gonna be heavier than automotive crankshafts. Because we use the crankshaft, we don't have a flywheel on an aircraft engine. We use the propeller partly as a flywheel, but we also use the counterweights on the crankshaft as a flywheel force. So this additional mass is going to make the engine run smoother. It's also going to allow it to keep momentum between every individual power stroke. Now these are forged. You all know, how many of you know the difference between forging and casting? 2, 3, 4 here. Okay, it's time for me to show you a movie then, which probably won't break your heart and you can see a movie. So forging is a method that we use to compress the metal. And what we do is we press it into shape. Casting, we just pour the metal into a mold, and what we get is what we get. So early crankshafts were cast, and they worked out pretty good, but once the forces got to be higher and higher in the engines, and the crankshafts got longer and longer, they wanted to twist more and more. So now you needed a crankshaft that was a lot stronger. So by forging a crankshaft, in fact, most parts that are forged are going to be stronger. Most everything is forged anymore, unless it absolutely is cheaper to build it as a cast part. But let me show you a little video here, and this is going to explain forging pretty well. In fact, it's a crankshaft. It's at a Ford crankshaft factory somewhere in the Midwest. Pull this up here. That's it. Now, it's got a terribly large display. Let me turn the picture here, the lights down in here. Where we're going to go here is process. Don't worry, I'll back this up once I get my ducks in here.
Upsetting regions along the length to greater sizes than adjacent regions, or bulging the workpiece's cross-section while reducing its length.
Down to the bottom of that box.
Okay, here we go.
The workpiece's cross-section while reducing its length.
You can see there's some pretty heavy equipment involved here. Now this is just an axle for a train. How's that for an exciting job? Do that for 30 years.
The forging process at Woodhaven Forge starts at the steel receiving. Steel trucks deliver steel around the clock to keep the process going. Here, you can see an operator loading steel off the truck and putting them into the storage racks. From the storage rack, the steel is loaded onto the shear table. Induction heaters are used to heat the steel to avoid stress cracks in the billets. The shear cuts the steel bars into individual billets, each weighing approximately 100 pounds. The billets can be processed into tubs for future use, or be sent directly up to the next process. A bowl feeder system is used to process the billets into the induction heaters, which heat the billets over 2200 degrees Fahrenheit. At this point, the billet is the correct size and temperature and ready to be forged. The billet is now ready to be processed. This is the roll forming operation. As you can see, the hot billet comes in around, but leaves with a toe bottle shape after going through the 2 die stages in the roll form. The purpose of the roll forming operation is to redistribute metal to reduce the amount of work which is to be done in the main press. Conveyors bring the rolled part to the main press operator. The operator sets the billet into the blocker, cycles the press, then flips the crank into the finisher die. After the press cycles again, the operator flips the part onto the T5 cart to be sent to the trim press operation. Watch the different views of the operator shaping the hot billet into a crankshaft.
State-of-the-art crankshaft forging operation at Woodhaven is a landmark in the industry. Woodhaven has best-in-class quality and safety records, unparalleled in the crankshaft forging industry. After the crankshaft is forged at the main press, the T5 conveyor takes the forging to the trim press. The forging is loaded into the trim press by the HR1 robot. The trim press removes the flash from the part by using a punch and blade die. The flash stays on top of the blade while the part is punched through. The flash is taken off the blade by a flash removal robot. Strap conveyors take the flash to outside hoppers. Eventually, the flash is remelted at another port site and made into other engine components. The HR2 robot loads the trim part into the twister. The twister is used to put the pins and counterweights into the proper position. The calibration press precisely strengthens the crankshaft. This reliable piece of equipment is one of the big contributors to Woodhaven quality. The calibration press tonnage monitor is an example of proactive thinking as it prevents damage to the press. The crankshaft is placed onto the cooling conveyor by the WMP robot. The crankshaft is cooled for 2.5 hours before it is processed by the finish line. A coordinate measuring machine is the main method used to verify that the crankshaft is within part trim specifications. 1 part per hour is measured on this highly accurate machine. Parts arrive at the finish line via the cooling conveyor, or they can be manually loaded as shown here. The bucket conveyor takes the crankshaft into the paintborne shot blast machine, which thoroughly cleans the crankshaft. After the part is shot blasted, it is removed from the shot blast machine by the V-block conveyor. The pick and place unit removes the part from the V-block conveyor. The orientator then positions the part for the next operation. A chain conveyor takes the part to the KJ log bend gauge. The KJ law bend gauge measures the amount of bend in the part then accepts or rejects it based on part specification. A magnetic particle inspection booth is used to find otherwise imperceptible defects. The crankshaft is magnetized and sprayed with a special fluid that shows up bright yellow under the ultraviolet light. Here, a crank with a lap is detected by the operator and marked for further repair. An inspector gives the crank the final approval to be shipped. The parts are manually removed from the conveyor and placed in shipping containers. A fork truck removes the basket and places it in the ready-to-be-shipped area of the plant.
Pretty simple, huh? For a crankshaft, is forging. Okay, so what we're doing is we're compressing the metal, compressing the molecules, makes it stronger. And then that kind of depends on the type of metal you use too. So most crankshafts now are made of 4340 or 4140 steel. They have a lot of nickel in them. They are pretty resistant to corrosion, which is something we're looking for in airplanes. Go just a couple more here and I'll give you a little break. Okay, so they're forged from chromoly steel, chrome molybdenum steel, or chrome nickel steel, or vanadium steels. The journal areas might be hardened by nitriding. So you all remember nitriding from your cylinder days. It's a process. We introduce ammonia gas across a hot surface, and it creates a hardened surface down to about 15 or 20 thousandths of an inch. Now, crankshafts can't be straightened, not in airplanes. They can in automobiles, but you may not straighten them in airplanes. So if you have a bent crankshaft, you get what you get. Okay. How would you bend a crankshaft?
Cross-train.
Cross-track, exactly right. Now, there are some repairs that you can do. If it is a flanged crank, you can actually shave a small amount of metal off the flange to straighten it up, but it's much less than 5 thousandths of an inch, just very little. Okay, so we talked about nitriding on the cylinders already. Same thing on a crankshaft. So we can grind into the crank surfaces, into the bearing surfaces. In fact, I should get one out. I'll tell you, why don't we stop there and I'll go get a crankshaft. Why don't you take 15 minutes, come on back about a quarter till, and we'll press on with the crankshaft here.